we have been investigating optical receivers. We saw that in photodetectors there are various mechanisms by which the noise is created. For example, there is the short noise because of the random fluctuations in the photon flux and the interaction of the photons with the matter, and there is the noise because of thermal movement of electrons inside a resistor. And then in the last lecture we saw that because of this noise we have deterioration in the system performance, and for a digital communication system we measure this deterioration by a parameter what is called the bit error rate. So, we have defined a quantity what is called the Q of the data, and which we have said is defined by this, where I1 is the photocurrent corresponding to the level 1 of the data, I0 is the level 0 of the data, and sigma 1 and sigma 0 are the standard deviations of the noise when the level is 1 and when the level is 0. We have also seen that this quantity is related to the noise margin of the data, because I1 minus I0 essentially gives you the swing between the two levels, and sigma 1 plus sigma 0 that gives you essentially the encroachment in this swing because of the noise. So, this quantity Q essentially determines the quality of the data which we measure in terms of the bit error rate. And we have seen that assuming that the noise is distributed in a Gaussian fashion, we can calculate the bit error rate, and we saw that if we plot the bit error rate as a function of this parameter Q, then the bit error rate decreases very rapidly as the function of Q. And if you take a standard number for bit error rate which is 10 to the power minus 9, then we require the Q at least to be 6. So, for a satisfactory performance of a receiver, this parameter Q has to be greater than or equal to 6. Today essentially we are going to look at the aspects what is called the minimum average power required in the data. We will also talk about what is called the quantum noise of the signal detection, and then we also talk about what is called the eye diagram, which gives you the quality of the data. So, essentially what we are doing here is we want to ask, if you are getting a random data with a equal probability of 0 and 1, then what is the minimum average power required, because that is what essentially one can measure. When one is receiving signal from an optical fiber, one can put an optical meter to measure the power which is coming, and this is essentially the average power which you receive in the signal. So, without losing generality, if we say that corresponding to the 0 level no power is received, and corresponding 1 level we have a certain power received, then the average of these two levels essentially gives me the power which the power meter will measure. So, let us say to calculate the minimum average power, let us say we have some power received corresponding to 1 level, and let us say for 0 level there is no power received, but without losing generality let us say some P0 power is received when our level 0 is received. So, let us say I have power P1 corresponding to 1 of the bit, and I have power P0 corresponding to 0 level of the bit, and the corresponding currents which you are going to get for these two levels are, let us say, given by I1 and I0. So, we have here I1 that will be equal to the responsivity of your detector multiplied by this power which is P1. Similarly, we can have I0, that will be responsivity of the receiver multiplied by this power P0. And for an ideal receiver, we are saying that since no power is received during 0 bit, this quantity is 0. Then one can define the average received power which your power meter measures, which we can call as P bar received. So, this is the average received power and which is the mean value of the two powers which you are receiving. So, that is P1 plus P0 upon 2. And in this case, since we are assuming that the power corresponding to 0 level is 0, this quantity is P1 upon 2. So, that means we have now the P1 power received is 2 times the average power received P received. So, we have from here P1 that is equal to 2 times P average received power. We can calculate the noises corresponding to these levels. So, when we have a 0 bit reception, that times since there is no optical power incident, only thermal noise is present. So, we can write down noise for 0 level. We get the noise variance which is sigma 0 square, that is nothing but equal to sigma t square, which is thermal noise variance, while in this case the optical signal is 0. Then for the 1 bit, the variance sigma 1 square, that will be equal to the sum of the variances because of the thermal noise and because of the short noise. So, essentially this will be equal to the short noise square plus sigma t square. Of course, depending upon the power level which we are receiving in bit 1, the sigma t may be negligible compared to sigma s or may not be negligible. So, in general we can write down the variance of level 1, that will be sum of the variances of the short noise and the thermal noise. And we have seen that this quantity here sigma s square, that is given by 2 times q, where q is the carrier charge, into responsivity into P1, but we have seen that the P1 now is 2 times this P average received. So, we can say that this is 2 times P average received and the bandwidth of the receiver. And as you have seen, sigma t square, which is a thermal noise, this is given by 4 kTb divided by RL, where RL is the load resistance connected to the photodetector, and K is the Boltzmann constant, T is the temperature. Once we get these quantities now, so we know these levels I1, I0 and I0 is 0, and we also know this quantity sigma s and sigma t. So, we can now define the quality factor is Q, that is equal to I1 minus I0 divided by sigma 1 plus sigma 0, and since I0 is 0, this is essentially I1 divided by sigma 1 plus sigma 0. Substituting for I1 and sigma 0 and sigma 1, we get this is 2 times responsivity to P received average divided by sigma 1, which is sigma s square plus sigma t square to the power half plus sigma t. We can reverse this expression to get the received power in terms of this factor Q. So, we can get this quantity average P received, that will be equal to Q divided by the responsivity into QB plus sigma t. Note here in this quantity sigma s square, when we are talking about, we are already having a P received. So, essentially you have to solve for P received, and this is what we have done to get this quantity P received. So, now we are having the P received, which is expressed in terms of this parameter, which is Q. And we have seen for the acceptable bit error rate, the Q has to be greater than 6. So, now we can substitute the value of Q, and essentially we can calculate what is the minimum average power required in the data to achieve the required bit error rate. That is, of course, one can do depending upon the parameters, one can do the quantitative calculation. But the thing which we see from this expression, the interesting thing is that now, as we saw in the last lecture, we can have the two regimes. One regime which we call as the thermal noise dominated regime. That means, if the optical power is not very high, then the short noise is negligible compared to the thermal noise, and then we say that this regime is the thermal noise dominated regime. In second case, when the optical power is significantly high and the variance of the short noise is much larger compared to the variance of the thermal noise, then thermal noise can be neglected, and then we can say that regime is the short noise limited regime. So, same thing we can do here. So, in this case, if we take the thermal noise dominated regime, then we can, this quantity now is very small. So, we are having only thermal noise which is present there. So, we can calculate the minimum P received, P REC, that is equal to Q into sigma t divided by the responsivity R. And by substituting for sigma t, which is proportional to square root of B, essentially we can get the P REC, which is proportional to square root of the bandwidth. And since the bandwidth is directly proportional to the data rate, essentially what we are saying is that in the thermal noise dominated regime, as the data rate increases, the minimum power required to achieve the required bit error rate has to be increased, and the increasing that power is proportional to square root of the bandwidth. So, the requirement of the power increases, but it is not very rapid because it is going to increase as the square root of the bandwidth. So, if you are having an optical communication system and if the signal has travelled over a significantly long distance, so that the detected power is much smaller compared to the thermal noise contribution, then we can make this approximation that now the regime is thermal noise dominated regime, and in that situation for long link, the minimum required power to achieve a given bit error rate would scale as square root of the data rate or the bandwidth. Whereas, if you go to the other extreme, where the receiver is reasonably close to the transmitter, and in that case there is no significant attenuation of the optical signal in the optical fiber, then the power which is detected by the optical receiver is relatively large. and in that case we may get the short noise, which may not be negligible compared to the thermal noise, and in that case this regime will be applicable. So, we have the second limit, which will be short noise dominated, and in this case this term is negligible now. So, we can get this quantity. So, this P received, that is equal to your Q B Q square divided by the responsivity R. So, what we find in this case now, that the P received for a given value of Q is proportional to the bandwidth. So, this quantity now is proportional to bandwidth. So, for the low optical powers, the minimum required power scales a square root of the bandwidth, whereas if the optical power is large, then the minimum required power will scale proportional to the bandwidth. That means, as the bandwidth increases, you have to increase the power in the same proportion to achieve the same bit error rate. So, in fact, what the analysis is telling you is that when the different data rates are transmitted on the optical communication system, depending upon the separation between the transmitter and the receiver, the minimum required power scaling will vary as a function of bandwidth. So, for the receivers which are separated by a large distance from the transmitter, the minimum required power will scale a square root of bandwidth, whereas if the receiver is nearby to the transmitter, then there is a good possibility that now the short noise will dominate, and in that case the minimum required power will scale as the bandwidth. So, in fact, in this case now what is happening is that the power which is to be transmitted and the bandwidth, they are related now. So, we cannot arbitrarily increase the bandwidth without increasing corresponding power, otherwise we will not get the required bit error rate or the system performance. So, now one can ask a question that if we had designed a receiver, the best possible receiver, that means if we make a receiver where thermal noise is negligibly small and whatever noise is going to be there is going to be purely because of only the photon fluctuation, then what kind of minimum power I require or minimum number of photons we require per bit to get a required bit error rate. So, this is the ultimate performance on the limit one can get on the optical receiver, that is in the absence of any external noise, that is the noise created by the amplifier or by the resistors, that is thermal noise, just because of the intrinsic nature of the photons, which is statistical. What is the minimum number of average photons required per bit to achieve a required bit error rate? And that limit is what is called the quantum limit of detection. So, idea here is as follows. We simply now take the statistics of the photon into consideration, and that is the Poisson statistics, and then you ask that if the thermal noise was not present, then what is the average number of photons required so that there is no bit error. So, since we are assuming now that the thermal noise is completely absent, when 0 level is transmitted, no power is transmitted optically, also there is no thermal noise present. So, no power was transmitted, no power is received. So, there is no possibility of having a now error in detection of the 0 level. However, if certain power is transmitted by the transmitter, but no power is received, and in this case we are saying since thermal noise is absent, even if one photon was received during the bit 1, then we say the bit is detected. because now there is no error in detection of 0. That means, if no photon is detected, we say that level is 0. So, even if one photon was detected in one bit, then we say that the bit is present. That means, now what we are saying is, if some average number of photons are transmitted per bit, what is the probability that not even one photon is received during one bit duration? Because if that happens, then the one bit will not be detected as one bit, it will be detected as 0, and then we will have a bit error. So, in this case, when we are assuming there is no thermal noise present into the system, there is no bit error corresponding to 0 level, and there is a bit error corresponding to only 1 level. So, now let us say we have a power transmitted during one bit, and as we have seen, the power might fluctuate as a function of time during the one bit. So, we can say that if some PT power was transmitted during one bit, the number of electron hole pairs generated N, that is equal to some parameter which we call as quantum efficiency divided by energy of one photon, which is h into f, where f is the frequency of the photon, and you integrate the power over the bit duration, which is 0 to tau, and this is the power which you are getting as a function of time during the bit. So, we are assuming in general the bit is not necessarily rectangular, it may have some variation like this, and that is what is represented by one level. So, if you integrate now the power over this duration tau of the bit, that gives us the total energy in this bit. You divide by the energy of one photon, that gives you a number of photons which are received by the detector, and multiplied by the quantum efficiency, that gives you the number of electron hole pairs generated. Now, as we have seen that this quantity n is essentially telling you the average number of electron hole pairs which will be generated during this time. That is because the photon flux has random fluctuations. The photon arrival process itself is a statistical process. And as we have seen that this process is a Poisson process. So, now one can ask a question that if on average n photons were received by the detector or were supposed to be received by the detector, what is the probability that not even a single photon is detected by the receiver? Because if that happens, as we said, there will be bit error in detection of the bit 1. So, the probability function for the Poisson distribution is given as, so you have a probability of n small n EH pairs generated during certain time. Let us say that is given by P n. That is given by the Poisson distribution, which is n to the power n, e to the power minus n divided by factorial n. This is the Poisson process. So, now as we said that the one level will not be detected as one level if no photon is received during this time. Even if one photon is received, we will declare the bit is present. That means the bit error will be committed only when no photon is received during a given time period for the bit. So, now we can ask a question, what is the probability that when n average photons were supposed to be received by the receiver, no photon actually was received. That means n is equal to 0. So, for quantum limit, we are saying that what is the probability of receiving 0 photon or no photon in that bit duration, which is P0, that is equal to n to the power 0 e to the power minus n divided by factorial 0, which is e to the power minus n. And we have defined a standard that our bit error rate should be less than 10 to the power minus 9. That means this quantity now should be less than 10 to the power minus 9. So, if we equate this to 10 to the power minus 9, we get this average number of photons which must arrive during 1 bit duration, and that will be approximately equal to 21. So, what we are essentially saying is that if the thermal noise is absent, if the fluctuations are because of the statistical nature of the photons, then there must be at least 21 photons on average guaranteed per bit. Then there will be a chance 1 in 1 billion that no photon will be received during that bit duration. Of course, in practice, we do not work very close to this number. The number n is rather large. Typically, it could be of the order of about few hundred to 1,000. But this is the ultimate limit which one can get on the receiver performance. So, even if you make the best possible receiver, which does not contribute any additional noise because of the thermal nature, even then, just because of the statistical nature of the photon arrival, we need to guarantee 21 photons per bit to get a bit error rate of 10 to the power minus 9. And there is a very interesting result, because what then it is saying is, it is not saying that the average number of photons in the data should be so and so. It is saying that in the bit duration, the number of photon must be equal to 21. Or in other words, as the data rate increases, the bit duration becomes smaller and smaller, and for getting the 21 photons on average during 1 bit period, you get more and more number of photons per second, because there are now more and more number of bits are going to be per second as the data rate increases. So, essentially what we are saying is, as the data rate increases, now we are having now proportionality between the number of photons per second and the bandwidth. And that is what we saw in this case here, that when we are having a short noise dominated regime, and that is what we are talking about, because in this case we assume that the thermal noise is practically absent, and in that case then we get a proportionality between the number of photons required and the data rate, number of photons required per second and the data rate. And number of photons required per second, if you multiply by the energy of the photon, essentially we get the average power which is going to be there in the data. So, this is what is called the quantum limit of detection, and for data rate, let us say about 100 megabits per second, typically the quantum limit would be very, very small. It will be typically of the order of about minus 70 dBm or something like that. But in real system, the thermal noise is of the order of about minus 60 dBm. So, normally we do not really go into the regime of really the quantum limit of detection, but if it happens in future, if you could make better receivers, then we would be dealing with the quantum limit of the detection. So, this is one of the important aspect of the detection of the data and the corresponding bit rate. Another aspect which you have for the optical receiver is what is called the inter-symbol interference. Now, inside optical receiver, as we have seen, there are resistances and capacitances. So, essentially an optical receiver behaves like a low pass filter. That means, if you receive a very sharp transition in the optical signal, your optical detector will not be able to respond to that sharp transition. It will blur that transition because you have a finite bandwidth, and because of that the rise time of the system is limited. Also, because of this finite bandwidth, in the time domain we have the ripple in the signal. So, what we are saying is, if ideally if we had transmitted a pulse, optical pulse which was like this, and if the bandwidth of the system was infinite, you would have got a current pulse also which would look like that. However, because of the finite bandwidth of the receiver, the pulse firstly will get blurred, so you will get slow transition like that. But in addition to that, you will also see that there is some fluctuation of the signal which is going to be taking place. So, the actual data pulse which you receive is going to typically look like that. Obviously, this signal which ideally should have been 0 now is having these fluctuations. So, if you have another bit present at this location, this signal is going to superimpose on this. This phenomena is what is called the inter-symbol interference. So, we are transmitting this bit, and this bit is now going to create an interference at another bit which is separated in time. So, if you are having now the random bits received by the receiver, then we will not get the data which will look as clean as this, but which will be superposition of this. Again, this bit also is going to get distorted in a similar fashion like this. So, essentially we are going to get some fluctuation even at 0 level, which ideally should have been 0, plus some deformed pulses in the data. So, when arbitrary data is transmitted, essentially we are having a situation which would look typically like that. And now what we are saying is, here we do not really integrate the optical power received inside a pulse. The pulses are converted into corresponding photocurrent and the corresponding voltages, and then you are having the duration or the location in time where we are expecting a bit. So, what the receiver essentially does is that at that instant of time, it simply checks the value of the voltage or current. If that value is greater than the threshold value, then it declares that the bit is 1. If that value is less than the threshold value, then it declares the bit is 0. So, these are the locations where the samples are tested for the signal level, and depending upon the amplitude of the signal at that instant of time, the bit is either declared 0 or the bit is declared 1. So, now in the presence of these distortion which you are going to get in the pulses, essentially if you are having the pattern which looks ideally like that, the actual signal which we will receive will be something like this. So, as you can see here, even that one level could not be reached, because before it could really rise to this value, the bit has already gone to 0. So, signal start decreasing again. Similarly, before this signal could reach to 0 level, again the one next bit is coming, so again signal start rising and so on. So, actually signal which we receive from the receiver, that signal essentially will look something like this. So, we want to create now a mechanism by which we can measure this distortion which is going to be there in the data. So, let us now consider all possible transitions which the data can go through. So, let us consider, let us say 3 consecutive bits. So, we have various possibilities, either we can have 0 0 0 bit, or we can have 0 0 1 bit, or we can have 0 1 0 bit, or we can have 0 1 1 pattern, and so on. So, these are the 8 possibilities if you consider a pattern of 3 bits. And if this pattern is passed through the optical receiver, then at the output we will get the signal which will look something like this. So, if the bit pattern is 0 0 0, then the level will remain 0 like this. If the bit pattern is 0 0 1, then it will remain 0 here, but then it will start rising. So, you will get a function which will look like that. If you have a pattern which is 0 1 0, then you will have this edge, then you will have this edge. So, you will get signal which will look like that. If you are having 1 0 1, then this is 1, this is 1. So, signal will decrease, but before it reaches to 0, again the 1 has come. So, you will get a thing which will look like that. And if you are having pattern which is 1 1 1, then it will remain practically flat on the top of this. So, if we assume that now the data is coming randomly and any of these patterns, let us say, is present with equal probability in the data. Essentially, sometime we will have this, sometime we will have this, sometime we will have this, and so on. That is what essentially we are going to get. So, if you look at now the data stream in general, it may look something like this. So, here this is the bit pattern which is 0 1 0, this is 1 0 1, and this is 0 1 1, this is 1 1 1, this is 1 0 1. So, actual data which are received will look something like this, and these are the blocks of 3 bit patterns. So, now we want to find out the quality of the data, that means how much distortion has taken place because of the finite bandwidth of the receiver and also due to the presence of noise. So, in this case we saw that the bit is distorted because of the finite bandwidth, but now the bit is going to have additional noise also which is present on this. So, actually the signal which will go something like that. That is the way the pattern will be received. So, when we are talking about a pattern which looks like that or a pattern which looks like this, the noise also is going to be superimposed on this, and in general the noise would be a function of the amplitude if the short noise is playing a role. So, we will have the signal which we receive which will look something like this. So, now to measure the quality of the data, we use a technique what is called the eye diagram of the data. And here idea is as follows: we have a simple setup. So, this is the measurement setup for what is called eye diagram. So, what we are essentially doing here is that we have a transmitter here which generates the data in a random sequence. This data is supplied to the optical receiver which you want to test. The output of this receiver is given to the oscilloscope, and the clock with which the data was generated is supplied as an external trigger to the oscilloscope. So, essentially now this data which we are recording on the oscilloscope is synced with the clock of the data. As a result, what will happen now is that we get now the folding of this data over 1 bit period or let us say 3 bit periods. So, as the data stream is coming, we have this pattern which is there. If the data is synchronized with the clock, we essentially see superposition of all these blocks, this block, this block, this block, this block, and so on. So, sometime we have a variation which will be like that, sometime we will have a variation which will be like this, sometime we will have a variation which will be like that, sometime we will have a variation which will be like this, sometime we will have a variation which will be like that. So, if we synchronize the oscilloscope with the clock, then essentially we get the output on the oscilloscope which would typically look like that. This is what is called the eye diagram of the receiver. And why it is called eye diagram? That if you look at this pattern, it looks similar to the eye, and that's the reason this pattern is what is called the eye pattern of the data. So, as we saw there, we have all possible transitions which are going to take place. So, you may have signal which will continue like this, or you may have a signal which may make a transition this one, or we may have a transition which is like this, and so on. So, that is what is shown here, that if the data is received from the optical receiver and if it is synchronized with the bit, then we get a pattern which will typically look like that. So, you will have, this is the thing which is going from 0, 0, 1, the pattern will look like that. If I consider 1, 1, 0, the pattern will look like this. If I consider 0, 1, 0, pattern will be this. If I consider 1, 1, 0, 1, 0, 1, the pattern will be like that, and so on. And now this dot which you see here are just the fluctuations in the optical intensity because of the noise which is present there. So, this pattern essentially gives the visual feel for the quality of data. So, now the parameter which you want to extract from the eye diagram is the parameter which essentially can be used for calculating the bit error rate. And we have seen that the bit error rate can be calculated by using a parameter which is Q, which depends upon the difference between the two levels 1 and 0, and also the noises which are present. So, now if I take the mean value of this level here, this essentially corresponds to the level I1. Similarly, if we consider this level here, this level mean level essentially corresponds to level I0. So, measuring now the average value of this and average value of this, we can calculate this quantity I1 minus I0. Also, knowing now the maximum deviation which we get from here to here, we can calculate now the variance of the noise corresponding to level 1. Because if we assume that this distribution is almost Gaussian, then the peak to peak spread will be typically about 5 to 6 sigma. So, if we measure this peak to peak deviation from here, 1/5 of that approximately gives the value of sigma 1. So, measuring now from the oscilloscope the peak to peak deviation, we can calculate the quantity sigma 1. So, we are saying that this quantity here, this one, this is approximately equal to 5 times sigma 1. Similarly, if we consider the peak to peak level here, this one would correspond to 5 times sigma 0. So, from the eye diagram we can calculate this quantity I1 minus I0. We can also calculate the quantity which is sigma 1 plus sigma 0, and once I get that, then we can calculate the parameter Q, and then we can go to the plot for BER and then calculate what is the BER for this optical receiver. Invariably what people do essentially is they define some kind of a mask which fits into this eye diagram, and they run the receiver for a very long time and just measure how many times the noise has fallen inside this mask, and that essentially gives the measure of how good the data quality is, because ideally it should have remained, noise should not have encroached into this region, and wider this range, better is the quality of the data, because lesser will be the probability of the bidder. So, now we see that as the signal to noise ratio, which is essentially the quantity Q, as the signal to noise ratio reduces, this level essentially reduces, I1 minus I0 reduces. So, the eye starts closing vertically. So, any reduction in the amplitude of the eye or a closing of the eye vertically reflects the reduction in the signal to noise ratio. What more the eye diagram gives? We see that since we have synchronized the data with the clock, essentially this period from here to here will be 1 bit duration or 3 bit duration. So, if this clock or the data is coming with an absolutely constant clock, or on the receiver side when the data is received, we generate the clock from the data, we will see later, and then if this clock is perfectly stable, we will see that these points are very steady points, they do not change as a function of time. But suppose there is a small jitter in the clock, that means the two frequencies of the data and clock are not same, then these points will slightly wander around this point. So, the width which we see in the horizontal direction for the eye diagram, that is a measure of the clock jitter in the data. So, we can take the deviation from this direction, and that essentially is what is called the tau, which is the clock jitter. Clock jitter is the random fluctuation of the clock with respect to the data, and because of that, when we try to sync the data with the clock, this period is not perfectly synced, and because of that we have a random fluctuation in this point. So, essentially eye diagram gives two parameters. One is the signal to noise ratio, which is related to the bit error rate, and also it gives you the clock jitter, because the clock jitter tells me how precise my sampling point should be. Ideally sampling point should be in the middle, but if the clock jitter increases, then essentially this region becomes wider, and because of that the eye starts closing horizontally. So, we see the eye diagram essentially gives the quality of the data for signal to noise ratio, and vertical closing of the eye indicates the reduction in signal to noise ratio, whereas horizontal closing of the eye indicates the clock jitter. And any of these situations when happen inside a receiver, you have essentially performance deterioration. So, eye diagram is one of the very important diagrams. After the system is designed completely and commissioned, essentially one has to perform the final test on the data, which is what is called the eye diagram, and then only one can satisfactorily say that the optical receiver is performing satisfactorily. So, these are certain tests which are conducted on optical receiver, and the parameters are extracted to calculate the quantitative parameter, what is called the bit error rate. Now, up till now what we have done is we have assumed the optical receiver to be ideal, in the sense that when we say 0 level, no power is received by the optical receiver. So, there is no what is called extinction ratio is 0, whereas in real data when we talk about these quantities will not be there. Also, the pulses which we transmit will not be rectangular pulses, they will be deformed because of various factors, and that will have its implication for the bit error rate. So, up till now we have considered the ideal systems. When we meet in the next lecture, essentially we will discuss what are called the power penalties. That means, if the receiver is not ideal, then how much extra power has to be supplied by the transmitter to account for those non-idealities in the receiver to achieve the same bit error ratio.